Hey gamers, welcome back to the Real Hacker Hours podcast. Today I'm going to be continuing the project of porting Nightmare from Python 2 over to Python 3. Today we're going to be looking at the buffer overflow call function, so leveraging a buffer overflow to actually call a specific function. For this, I'm just going to be going through the write-up, first making sure that the write-up makes all logical sense, since one thing that's come to light in the years since I've made this is I made a ton of typos, and then in any Python 2 portions I'm going to be porting them over to Python 3. So let's begin with Seesaw 2018 and get it. So let's go to the module. Where is it? Call function. Get it. Okay. Here is the write-up, and I'm just going to throw the binary into Ghidra real quick. Okay. Let's open it up. Yes, we want to analyze it. Okay, cool. So start off, run file and checksec on it, and then run it to see what we're dealing with. So let's go ahead and just do that real quick. Modules, I think. Yep, this is the fifth one. Get it? Sixty-four bit, partial railroad, no canary, NX enabled, no pi. Yep, this matches. Okay, see, this is what we claims the main function to be. So let's take a look at that. Okay, this matches this. So this is the main function here. We can see here it's effectively just calling gets into a local buffer. So we have a stack buffer overflow, since gets is always a buffer overflow, since there's no size limit. So we could control it. There is no pi, so the address of all of the segments of the binary, so like functions and BSS, they're all static. Here we see that there is a function called give shell, which is located here, so we can just call that. Let's make sure that this is what the write-up says. Run it with prompts until the main function, we can see that it makes a call to gets. I'm just going to take a second to read this to myself. Yeah, I think this is the first time in Nightmare I'm explaining like you leveraging a buffer overflow to overwrite the return address, so explaining that here, even though when I spoke I kind of just summarized it. Okay, made a typo there. So effectively, yeah, what this portion is it's just explaining, okay, we can overwrite the return address, but what's like the space buffer between the start of our input and where the return address is? There's like a million different ways you can see this. First off, we can look at here, we can see that local 28 is stored at minus OX28. And thing is, Ghidra, I believe they address all their offsets off from the return address. So minus 20, 28, that's 40. We can also use GDB. I'm going to set a breakpoint for this instruction. So effectively when this instruction gets executed, we will be able, it will just pause the program and allow us to, oh wait, do that. So right now we broke on this instruction, get scanned in our input. So what we can do is we can look for that input in memory. We see it is stored here, and we can look at the frame. Saved return address is stored here. Our input is stored there, or it begins to be stored there. We can take this, subtract. This is the start of the return addresses, which is where we want to start overwriting, and this is the start of the input, so our input has to be OX28 bytes, which is also 40 bytes. Just gonna double check and make sure that this is correct again. Yeah, this portion seems right. This function looks like it's just calling. Oh yeah, let's take a look at the give show. Yeah, just calling system bin bash. So if we call this, we solve the challenge, which is what this is saying. Okay, and this is the exploit, and then you run it. So this looks mostly. Oh, this does look good. No logical inconsistencies we're missing. So I just have to port this over to Python 3. So let's go ahead and do that. I am going to, instead of importing everything, let's just import process, GDB, and P64. This is good. This is good. GDB, yeah, that I'm gonna assume that type on the GDB script is still valid. We need to switch over from string to byte string. And that should do it. Let's see if I ported it right. Okay, it looked like it crashed into system. Oh, yeah, right now we're breaking on, the GDB script is to break on that instruction, which is, do we have the disassembly? Yeah, the move instruction. Reason why I had that GDB script there is when I was initially solving it, I just felt like dynamically looking for what the difference was, so I just threw that in there. Let's try running the scan. I'm going to break do system. We broke there. Okay, cool. So we can see that we're actually calling the do system function, but it's crashing somewhere later down. I believe it's crashing in system and backtrace. Yeah, it's breaking in the do system function, which is called in give shell, which if we disassemble this function, actually it's called in system give shell calls system, which calls do system. Now, why is it crashing? Thing is, with how Linux binaries works, a lot of them will rely on a libc library, which is just a common standard library of functions. Thing is, there are many different versions of the libc. I think they get released once a year or something like that. Thing is, this, yeah, This binary was made with one version of libc, which I'm running with a different one, and the thing is, when you try to do some exploit techniques like this, they aren't compatible. So a lot of times what you might, I've seen this a lot in various CTFs where like I'll call a win function, and because I'm running it with a different libc in a different environment than what's running on the server, I'll actually run the solution function, but it'll still crash. But when I run it into the actual target on the server that's running in a different environment, it'll run just fine. Here we can see that we're actually hitting the do system, or the give shell function, which logically speaking shouldn't give us it. And this is the actual solution I used to solve it during the CTF and get the flag. So we can see that it's working just fine in terms of what the solution should be. It's just because it's a different environment, it's crashing while it's trying to give us the shell. So I'm going to count this as solved. And also let's remove this core dump. Okay, cool. I'm just going to head and just actually, yeah. So we ported that over. I'm going to save this. Next up is func. Let's take a look at that. Okay. Let's throw it into Ghidra. Let's go ahead and analyze it. And while it's analyzing, I'm going to open up the write-up for it. Okay, cool. So let's go ahead and see what we're dealing with. Okay, 32-bit binary, 32-bit binary. I see that I did not run checksec on it, so I'm just going to copy and paste this portion in. For this, we see that it has NX enabled, so non-executable stack, but no pi, no stack canary, no raw. And when you run it, it gives prompts us for silver inputs and prints out this text. Looks about right. Okay, cool. So let's go ahead and take a look at the main function here, see what we're dealing with. Okay, prints out some text, runs scanf with local line ID. So what is this? Let's convert this over to char. Okay, that didn't work. Scans in, sleep, printf. So you can see that we're dealing with a 30-bit binary process with two separate first is union, second is a string that is supposed to be trust. Take a look at the main function. Yeah, that seems right. So you can see the program is effectively calls scanf twice, which it does. The input is first scanned into the name, and then into password. The format specified the stack for the format variable. You can see it's using the assembly code. This is %30s. Yeah, so this hex right here, it's effectively ASCII. It just represented as hex. You can see. Wait, no. What am I doing? Yeah, it's backwards. Percent 25, 33, 30. So what this string effectively maps to, since it's little endians backwards, is %30s, so allow us to scan in 30 char bytes into into the buffer, and okay, and it allows us to scan it in twice. So this is, let's go ahead and change the format string being %30s, used for both scanfs as we see, and we see it allows us to scan into buff0 and buff1. Okay, and we see that buff0 is 20 bytes. Looking at the layout of the actually, looking at the layout, we see a format string is above both of these. For a second, what I thought was going to happen, actually, no, sorry, got it wrong. Buff0 is above format string on the stack. We can tell that since the offset is further from the base, this buff0 being minus ox1d, format string being minus ox9. What the solution I'm pretty sure is going to be for this is we first scan into buff0 with 30 bytes of data. Difference between buff0 and format string, let's go ahead and take a look. ox1d minus ox9, ox14, so it is 20 bytes. Sometimes compilers like to throw in a little bit of a buffer space or something like that, so it's always helpful to double check. And we can send it to 30 bytes, so we can just straight up like overwrite what format string is with the first buffer overflow. And what I think what I would do is just overwrite with %s. That, my voice just cracked. That way, we can just scan an infinite amount of bytes with the next one, which is I'm pretty sure what I did here. I'm just guessing, let's see. Okay, there's some default password stored at minus ox31 name. And the right up here, I named the two buffers something different. Minus ox9. ox14 is 20. Given setup, I'll be able to code execution with either overflow value. Yep, overwrite format. This will allow us to specify much data. Code execution with ret. Yep, so that's exactly what I was doing with this write-up. But the function calls the printf function. Okay, and the print flag function just prints it. So let's take a look at how much. First, I set up right after the second scanf call. Better from the input. Our second input begins at which is ox31, and we can see that it's ox31 from Ghidra. From the return address. Also, one thing, the memory layout here, probably the reason is 4-byte values. So most address, with the exception of variable length ones, are addressed at 0. Yep. However, arbitrarily, just so it messes the limit when we review the memory. Putting it all together, we have the following exploit. So here, I overrode it with %99s. I'm just going to go ahead and change this to %s when I go ahead and port it. And yeah, so print flag. Okay, cool. So yeah, effectively looking over the write-up, it does exactly what I stated. Uses the first buffer overflow to overwrite the format string, which is stored on the stack, to a much larger value. So you can use a second buffer overflow to actually overwrite the saved return address, because with the default format string, we can do an overflow, but it's not large enough to actually hit the return address. I'm just going to go ahead and port this over to Python 3 and make sure it works. So process Actually, I'm gonna leave this as, no, target. What do we need? That, and this. B32, target, process. Yep, that should be everything we need. So establish a target process, receive and tell. I think this needs to be a byte string. This is the first buffer overflow to overwrite the format string. I'm just going to overwrite to %s so we don't have any length restriction whatsoever. Send the payload, receive and tell this. And this is the one to actually overwrite the saved return address with print flag. And that should do it. And let's see, does this work? Break at print. I'm going to break at this address. Hang on, something's break at OX 0804856B. Something isn't working here. Oh, I'm in the wrong. That was for Seesaw, get it. This is func, so let's go ahead and run this. Python 3 print. Okay, there's a print statement right here. I need to actually have parentheses since this is Python 3. And let's go ahead and do that. Print. There's also another print statement right here. Cannot import name target from Pwn. Oh, this is supposed to be process, not target. I always name the process target, so it sometimes gets mixed up in my head for importing. Cannot concatenate. Oh, yeah. Just a few mistakes. In Python 3 with Pwn tools, if you're sending data, it has to be a byte string. It can't just be a string like it was in Python 2. So I just had a mix up with the typing there. And we can see here, yeah, the flag does get displayed properly, so this exploit does work. Cool, I'm going to go ahead and change this. And let's take this. Okay, cool, so this one is done and ported. Let's go ahead and do the last one on this list for this module, which is Seesaw 16 warm-up. Let's go ahead and take a look. Is this the one I think it is? Oh, no, it's not. Warm-up Pwn checksec warm-up. Okay, cool. So we see 64-bit binary. I'm gonna copy this here since I missed the check sec for some reason. So you can see they're dealing with 64-bit binary. When you run it, it displays an address, looks like an address from the code section of the binary versus the section like the libc. I say that because a lot of the times the standard is for 64-bit binaries, especially with smaller binaries that you see in CTF challenges, the base will be OX4 followed by, I think, 5 zeros, 1, 2, 3, 4, 5. So a lot of the times, the address of like functions will be like what we see here, OX400060D, since the offsets from the base aren't that large. It is a small binary. Cool. So we see here. Oh yeah, that checks like I just copied over. And yeah. Okay, so yeah, we run it, gives us an address, looks like it's from the pi segment, and prompts us for input. And then next we look at it in Ghidra. Let's go ahead and do that. Let's go ahead and analyze it. Main. Okay, cool. So it prints warmup, writes the one here. Okay, prints the address of easy using sprint. Oh, writes it using sprintf to this buffer, which then will write to standard out. Okay, so what is this address? Easy. Okay, so this is the address that's printing out. So it's just printing out OX400060D, which is right here, the function of easy, which is being printed, and it is having a gets buffer overflow. So we should just be able to write, let's see, we should just be able to write OX48 bytes and then overwrite the address of the return address with OX40060D, and that should be the exploit. I'm just going to go ahead and read this just to make sure this makes sense, and it makes logical sense. Should be. Okay, so this portion basically explains, yeah, we're going to just use a buffer overflow to call the easy function. And this part we are doing to figure out the distance between the start of our input and the return address should be OX48 bytes. Yep, OX48. I'm just gonna add a part. We can find the offset in Ghidra. I'm just gonna add a part here that just explains. You can just look in Ghidra and find the offset. What did I name these? Input easy function address. I'm just gonna rename these to match the ones in the write-up. That way I could just copy and paste this in and it'll just make sense. Why is this? Input easy function address. can also find the offset from the start of our input to the saved return address in Keydrill. Gonna widescreen this so it formats nicely. At the start of the function, it will display the stack layout. It will address the okay. Just added this in little extra bit so we have we show multiple ways to get the offset, which is good. And then we have the exploit here, which I'm going to go ahead and port that real quick. Component port all, target process. Should just have to convert this over to byte array, which we did. And yeah, that should be it. Let's see if that got ported over correctly. Do I have flag.txt? No, something appears to be going wrong. What is it? Hang on. I'm going to attach GDB. Right now I have it breaking at this instruction. Where is that? Okay, right after gets is called. Okay. So let's see exactly what's going on here. Leave, return, steps into system. Okay, is it breaking it? So we are calling easy. Okay, it's breaking into system. So this is another issue that we had similar to the other Seesaw one. Due to the different environment I'm running in, so yeah, the CTF challenge that this is from is 2016, so it's running on one specific libc. I'm running this with, let's see, what version of it? 20.04, so I'm running it with a different libc since I don't have any weird mechanisms in place to swap out the libc file. As such, due to the difference in libc and environment, calling certain functions, like in this case system, in different ways, in the previous environment that this challenge is meant to be running in would work just fine. However, calling it in this environment would cause it to crash. For the running this solution against the actual challenge in the CTF would solve it. However, since this is a different environment, it's crashing while the solution is running. I'm running the win function, so I'm just going to go ahead and consider this solved. With that, we have reviewed and ported the 3 different modules from the buffer overflow to call function module. I'm going to go ahead and end this podcast here. Thank you, gamers, for watching.